Hello and a very good evening to the chairperson, reviewer and fellow listeners. Let me start with some introduction about myself. My name is ZulkiflyAziz, PresenterID11, and this evening I will be presenting PaperID9 titled Simulation of Triple Helmholtz Coils for Wireless Power Transfer in Photocatalytic Wastewater Reforming. So without further ado, let's get started. The concept and definition will be introduced in the first section, followed by brief literature review on the various reactor designs. The simulation strategy will be outlined in section 3, followed by the result and discussion section, and the final conclusion. The quality of water is a worldwide current issue of major importance. With the presence of contaminants of emerging concerns, or CECs, in wastewater effluents are becoming a rising challenge. CECs include pharmaceuticals and personal care products, hormones, and other industrial chemicals. Consolidated technologies for wastewater treatment can effectively remove those pollutants, but they are not broken down, but merely phase concentrated. AOP is the state-of-the-art in water and air treatment techniques aimed to make the world a better place by using the energy harnessed in nature or artificial source and turn it into a set of chemical reactions that can turn those organic pollutants into harmless inorganic salts, which can then be safely discharged into groundwater or be subjected to further treatment. One such promising technology is the photocatalytic reforming, or simply photoreforming. So the whole idea is a culmination of two concepts, namely IPT, inductive power transfer, and photoreforming. Photoreforming is a process which harnesses light energy and turns it into a chemical reaction to treat pollutants. So in essence, it is a light-induced electron transfer powered by wire-free electricity transmission method. So what is photoreforming? By definition, it is a process which makes use of light-induced charge separation in semiconductors to promote redox reactions, namely the oxidation of organic molecules or pollutants and the reduction of hydronium ion to hydrogen gas. The entire process occurs inside a reaction chamber or space known as the reactor, and the radiation source most often comes from artificial light source such as UV lamp. The classical reactor designs include classical annular reactor, annular slurry reactor, fluidized bed reactor, tube light reactor, and optical fiber reactor. In addition to the classical designs, most recent and state-of-the-art designs include microreactor, parabolic through reactor, spinning disk reactor, fountain reactor, and rectangular open-channel reactor. The list is by no means exhaustive, but to list them all here would be impractical. When high throughput and continuous operation is sought, classical annular reactor is perhaps the simplest and most efficient. Major issue with slurry reactor is in the catalyst itself, which exists as solid suspension, which introduces scattering and absorption inside the aqueous medium. This causes the reaction intensity to reduce exponentially with increasing amount of solid particles in the medium. Usually, the radiation is confined into a narrow strip and becomes negligible beyond 2 cm radius from the lamp assembly. Significant breakthrough is recently made by Coils et al., who proposed the concept of multiple miniature and mobile UV lamps distributed freely inside the reaction space, made possible by wireless power transfer technique. This addresses the issue of non-uniform radiation intensity inside the classical slurry reactor. However, two significant flaws are identified in the proposed design. Firstly, the mobile lamps are intermittently active and simply shut off when passing away from the electromagnetic field of the transmit coil. So in order to address this issue, triple Helmholtz coil pairs are proposed here to extend and improve uniformity in the flux coverage. Secondly, the slurry reactor design requires additional and costly post-processing stage in order to recover the catalyst particle from the aqueous medium. This is a well-known issue inherent in all annular slurry reactor design. To address this issue, the catalyst must be coated onto the miniature UV lamps. This approach will incur two benefits. Firstly, it eliminates the need for post-recovery stage. And secondly, it minimizes light scattering since suspended particles are already eliminated from the medium. The objective is to obtain an optimized coil diameter for a slurry reactor of 3 different cylindrical heights in order to generate a uniform flux density distribution simulated along the central column of the reactor. The design and simulation of the miniature UV LEDs will be discussed in separate paper. Numerical solution to the flux density distribution along the central column of a slurry reactor is obtained by finite element method. The numerical data sets are converted into a 5-number summary, which is minimum, maximum, medium, first quartile and third quartile, also known as the box and whiskers plot, to statistically represent the flux distribution along the central column of the reactor. The plot, which gives the most uniform of flux density, will be somewhat normally distributed with minimum skewness. The simulation of the pickup coil will be considered in different study. The solution for the flux density distribution is governed by the Maxwell's equations. The constraints and variables used in the finite element method analysis are summarized in the following table. The core material is made of water, since in actual reactor, the wastewater becomes transparent after dilution and shares similar optical characteristics as water. The catalysts are non-magnetic and used only in small quantity. Therefore, its presence can be ignored in electromagnetic simulation analysis. Since this is a finite element method, a spherical boundary is used to mimic an infinite air domain. Homogeneous multi-turn coil feature available in the Elmer FEM solver for electromagnetic is used to model least wire. Each pair of Helmholtz coil is connected to dedicated and similar power source. It is immediately evident from the box plot charts that all data sets are positively skewed, suggesting that the simulated flux densities are actually most greater than the median value along the central axis of the reactor. The calculated median value is around 1 millitesla, except for 80 centimeter reactor, where the median value is found to be around 0.5 millitesla. Its distribution is also the least skewed, suggesting weaker and smaller variation in flux density as coil diameter decreases and becomes relatively smaller compared to the height of the cylinder. This happens because flux from nearby coils augment and weakens when the coils are moved apart. A linear dependency is observed between the coil diameter and the height of the cylindrical reactor, as evident from the chart. Frequency-dependent characteristic of the coil inductive value is also observed as the frequency reaches 700 kHz, caused by parasitic capacitance effect, which adds a negative component and reduces the overall net reactant value. Equally important is the effect of mutual inductance, which alters the value of the pair inductance despite their similar physical characteristics. The effect of mutual inductance is theoretically expressed in the Newman's relation as shown in the following slide. The AC resistance showed an exponential increase once the frequency reaches 700 kHz and beyond. due to the skin and proximity effect. The induced eddy current causes non-uniform current distribution within the material and increases the cross-section resistance. Frequency sweep showed a roughly uniform distribution of around 1 millitesla when simulated along the central column of a 60 cm tall reactor with an optimized coil diameter of 15 cm. But weakened significantly as the frequency is increased past 700 kHz, again due to increased AC resistance associated with the skin and proximity effect. So in conclusions, numerical solution is obtained by a finite element method. Numerical solutions to the flux density distribution inside 3 Helmholtz coil pairs wound around a cylindrical quartz geometry representing a slurry photochemical reactor is obtained using the finite element method by manipulating the 3D model and solving in 2D in order to save runtime and computation costs. Quantification by 5-number statistics. As visual observation can sometimes be quite overwhelming, it has been demonstrated here that the uniformity in flux density inside a cylindrical column can be easily quantified by representing each large data set with a 5-number summary consisting of the maximum, minimum, median, third quartile value, and first quartile value, followed by visualization using the box and whiskers chart. Once an optimized coil geometry is obtained, the miniaturized floating receivers can be properly engineered for the chosen geometry. Thus, a seamless and uniform distribution of light irradiation can be realized inside an annular slurry reactor, leading to higher conversion rate of pollutants and increase in yield. That is the end of my presentation. Thank you for listening.